diffusion models. So now we're switching gears, right? We've been talking about language models, which are, in this case, text-to-text models. I give text input and I get text output. And now we're going to talk about diffusion models. These are models that can be used to generate random images, or they can be a component of a text-to-image system, where I give a text input and I get a generated image output. So we'll follow the same pattern that we used for the previous sections here, where we'll start off kind of giving an overview of how diffusion's models work, again, at a super high level, just to kind of give you some intuition for like what these models are trying to accomplish and why the task is difficult and how they go about accomplishing it. And then in the next section, we'll talk about some of the most commonly used, again, closed proprietary models as well as open source models. We will see how to make API calls to use a closed proprietary model to generate images. And then we'll also see how to use an open source package to work with open source models in practice. So it turns out, again, Hugging Face has, just like they have their transformers package, they also have a package called diffusers, which is kind of very analogous to the transformers package for these diffusion models that are used for text to image. And so we'll see how that works. And all of this is very similar to what we did in the previous sections. You can almost map everything that we did now over onto a different class of models. Okay, so in this section, what do we want to cover? We want to cover, again, at a high level, what a diffusion model is, how diffusion models are used to generate images, how generation can be conditioned on text prompts, right? So when we introduce the idea of diffusion models, we'll start off just with these models that could be used to just generate random images. And then we'll see you can further customize those models to say, okay, don't just generate any random image, but generate an image that's sort of constrained by a given text input prompt. And then we'll talk a little bit more about what are kind of the most commonly used now form of diffusion models, which are called latent diffusion models. Because diffusion models on their own are actually fairly slow and inefficient. And so there was this kind of advancement in the area that led to a way to sort of speed up both image generation as well as model training using this notion of what are called latent diffusion models. So let's talk a little bit about how those work. And then again, this is meant to be a super high level presentation. There is an entire module devoted later on, once you get through all of the transformer stuff and all of the text-to-text model sections, that will go into much greater detail on how these types of models actually work. Here, we're just kind of giving you the first glimpse. Okay, so before we I guess get into too much detail here, let me actually draw something. I think this is kind of easier to explain on the whiteboard. So you can think of a digital image. Okay. Yeah, there we go. You can think of a digital image as basically just being a grid of pixels, right? So, if this is a rectangular image, I could divide that image up into a grid where each, grid cell is a single pixel, which is a single color, right? So this is one pixel here. A pixel is one color. And one color can be represented by a red, blue, and green intensity, right? So, this might be on a scale from 0 to 255. This is on a scale from 0 to 255. and this is as well, right? And so basically every single one of these pixels, I can specify the color with 3 numbers if there's no transparency in the image. And then I do that for every single cell in that array. So when it comes down to it, you can think of this image as basically just a big giant list of numbers, right? It's going to be the red value of the first pixel, the blue value of the first pixel, the green value of the first pixels, and the red value of the second pixel, and so on. So, you've got this big giant list of numbers that represent an image. And so the first diffusion models that were made to basically say, what if I wanted to generate random images that looked like coherent things? Like, what if I wanted to generate random portraits of people, right? Where when I generate the image, it's not an actual person, but it looks just like an actual person. Like, could I somehow train a model? Could I give it lots and lots and lots of examples of portraits of people, and then basically learn how to generate similar images that look just like they might not be any actual image or any actual individual in that training set that was used to train the model, but it looks just like them, right? And that makes sense that there are going to be some sort of like statistical regularities in the images that correspond to, say, pictures of people, right? Like somewhere here in the middle of the image, there's probably going to be, some sort of skin toned colored pixels. And if some pixel is a skin tone colored pixel, the pixel next to it is probably also a skin tone colored pixel. Then maybe on the outer edges, there might be some sort of like hair toned colored pixels. You get the idea, right? That these are not entirely random images, right? There's some sort of statistical structure to them. And so the idea behind, randomly generating images is, there are different ways you could think about doing this, but one way you could imagine doing this is I build some sort of model where I can just start out by generating a totally random image, right? So just all these pixel values are just totally selected completely at random, right? I just pick, say, random numbers between 0 and 255 for each of these values. And then I pass it through some sort of filter that's then going to map that to a new image that sort of has the same statistical characteristics as a portrait of a person. And so if I can build some model that does that, then I have a model that lets me generate random pictures of people, right? I start off with some totally random input, I pass it through this filter, and then I get as the output something that, has the basic characteristics of a portrait of a person. So it turns out that's like, okay, that's a nice concept, but it's much harder to do that in practice than that story makes it sound. And so, that's a cool idea, but it doesn't really work as simply as described. But with a slight modification, you can get this to work, right? So instead of saying, hey, I take a totally random input and I pass it into this model and I generate something coherent, what you can do is you can build these models that take a sort of noisy input and they produce a slightly less noisy output. It's possible to generate the training data to build a model that does that and then build a model that actually does it. And the way that you could do that is you could say, well, let's say I have this picture of a church here. I could take this picture of a church, this one that I have right here. I could add a little bit of noise to it, make it, it still looks like the same thing, but it's a little bit noisier. And then I could try to build some model that says, okay, given this as the input and given this as the desired input, can I sort of clean it up and generate a less noisy version of it? And if I can do that, I could then also do it at this level. I could say, okay, well, let's say I have a noisy picture of the church and an even more noisy picture of the church. Can I generate the sort of noisy one from the more noisy one? It turns out I can build these models that can kind of incrementally denoise images. That's something that's possible to do. And so the whole idea of diffusion models is you use this idea to ultimately build a sequence of models that can generate coherent images from just totally random noise, right? So I basically have these models that, at each step can generate a slightly less noisy output from the input, and it's trained on example inputs that are constructed by taking this image on the right, adding a little bit of noise to it to get this one on the left, and then trying to build a filter that can recover this one on the right from the one on the left. And so, the sort of an earliest diffusion models that came out were these models that were built to generate random images of specific types of objects, right? So this example that I show in the picture came from this church model. So this is like one of the classic early models where somebody took, built a data set that just had lots and lots and lots of pictures of churches, right? And they're these small color images of churches. They trained these, denoising models at each step. And then once you have those, you can then take completely random noise, right? Like, basically, what we were saying, just generating a random image over here. And then you can denoise it slightly to get something that looks a little bit more coherent, right? It's like almost like looking up at the sky and looking at a cloud and like, seeing a shape in it, right? It's taking total noise and finding something that maybe looks remotely like a church in that noise. And then you can take that one and you can denoise that a little more and you can denoise it a little bit more. And then in the end, you can produce this output that actually is a totally coherent uh, looking image of the a thing that looks like the images that you trained on. Although this actual specific church image might not have actually been one of the original images in your data set. Your models have essentially just indirectly learned how to generate random pictures of churches. So that's the whole kind of concept behind diffusion models, is that if you can build these models that can kind of incrementally denoise images, then you can generate random, and you build those models, to work with like, a specific class of inputs. Then you can build a model that you can just pass pure noise into it and then just incrementally don't denoise it one step at a time to get a coherent output. Um, and so that's the idea, is that diffusion models are used to generate sample images from some learned distribution of images. They do this in this incremental way where step by step they denoise a purely random noise. And yeah, so it's this iterative process where maybe over, say, 30 steps, you start off with pure noise and you eventually will end up with a clear image. So, what we're talking about here is what we'd call unconditional generation, which basically means, kind of the classic examples are cats. There's a cat data set and there's an open source model trained on that. There's a church data set. There's a celebrity data set. The idea is you take a whole bunch of training images that contain images of some type of object, and you build one of these diffusion models on that, and then you use that diffusion model to generate random images that look like the images that were in the training set. And so this is unconditional because when I do the generation, I'm not saying, oh, by the way, this time I want a brown cat or this time I want a gray cat. I'm not putting any restrictions on what I generate. I'm just saying, just generate a random image. Um, and so those are kind of the earliest diffusion models, or these ones that were capable of doing this unconditional generation, where they generate outputs that looked like the data that they were trained on. And the way you build these models is sort of this process where you start off with your clear images in your training set. You add a little bit of noise to them. And then you build a model that learns how to filter that image to get the denoised image back. And you do that at multiple levels, right? And so as long as you have lots of images of the kinds of things you want to ultimately generate, you can repeat this process for each one of them. And you can ultimately learn models that can do this denoising at each step. Um, and so once you do this, once you have such a model, then you can stick pure noise in the first stage, and then you can incrementally denoise to get your output. And so there's one specific model architecture. So just like the way we had the transformer with language models, there's one popular model architecture, which again, it's based on a deep neural network. This is something that you'll see more details on later. And that's this model that's called a unet. And so we'll see a diagram that kind of shows a high-level picture of what a unet looks like. But this is sort of like the analogous thing to our transformer that we saw for language models. This is a specific deep learning, or sorry, deep neural network architecture that's proven to be very useful for this particular task of learning this sort of filter for denoising these images that can ultimately be used for generation. And so the way this unet architecture basically looks is, you put an image in at the input, and so 128 by 128 maybe represents the resolution of the image. And so let's say it's 128 pixels by 128 pixels. And what it will do is it will downsample this, right? So it will produce a smaller image, it'll sort of abstract away some of the details of this image and maybe produce an image that's half the dimensions on each axis. To produce a 64 by 64, it'll downsample again, it will downsample again, it will downsample again, all the way till I throw away most of the information in the image and have a 4 by 4. It will pass it through some transformation, and then it will start with that 4 by 4, and then it will rebuild up a new image until it finally has one that's the original dimensions. And in the process of doing this, shrinking the image down and then expanding it back up, you'd say, okay, well, how could I ever expect to filter an image by throwing away almost all the information in it and going down to a 4 by 4 image and then trying to build it back up? You're also taking some information at each of these stages and passing it straight across to the block that will do that reconstruction. And so you're saying, okay, what's like the least amount of information I need to help the stage that's going to reconstruct this image back to 128 by 128? Let me pass that across, and then at some point when I come back all the way over to the right and I need to build a 128 by 128 image by a 64 by 64 image, I can take that additional information that's been passed over here and I can use that as input to help me recover my 128 by 128. So anyway, that's at a super high level what this is actually doing. These blocks that, this block in the middle and the downsampling and the specific types of things that are happening within that downsampling are details that we'll get into later. But the idea is that you have this model architecture that's ultimately used to sort of filter noisy images and can learn how to denoise images if you're looking at images within a specific class. If I say, here's a noisy image, but it's a picture of a church, what do you think it actually is? You can train these models to do that pretty well. Okay, so just like we had unconditional generation, then where this really starts to get interesting is when you have conditional generation. And so conditional generation allows you to say, okay, what if I don't want to just generate pictures of cats, right? Like, what if I don't want to give a model just lots and lots and lots of pictures of cats and then only be able to generate pictures of cats, but instead I want to give a model lots of diverse images. And then after training that model on lots of diverse images, at generation time, I want to be able to control which one I generate, right? I could say, okay, you've seen lots of things. You've seen cats, you've seen churches, you've seen people, you've seen celebrities. Now I want a cat. Now I want a gray cat, right? Like I want to provide this additional information and to condition my model. So it turns out that conditional generation is possible by extending our unet model to allow for some additional external inputs for guiding the image generation. So that might come in several forms, right? It could be text, right? We'll see that one way to do that is to provide a text input to the model. You can also give other images to guide it, right? So you might say, hey, generate a picture of a person, but I want them to look like this person here, right? And that could be an input that could ultimately condition or restrict how I generate so that I can, sort of limit exactly what's generated, um, even though I've trained my model on a really diverse set of inputs. And so if I wanted to extend my unet model to do this, say, for example, to work as a text to image model, what I can do is I can couple some things together. I can couple what's called a text encoder, which is sort of like a transformer-based language model like we saw before, with my unet, right? So basically this says I can put in a text input. I've got a model that looks sort of like our language models, our transformer-based language models that we saw before, that will produce some sort of encoding of that text that's meaningful to my unet model. And then I can feed that as an input to my unet, and that can guide the generation. And so if I train a model with lots of examples of pictures as well as captions of what those pictures are, I can train a text conditioned unet instead of an unconditional unet. Now that lets me actually provide inputs that can guide that generation. Okay, so before we go on, I see somebody had a question about when the class will end. Do you think we'll wrap up at 4 or go on till 5:15? I think it's more likely we'll go on closer to 5:15. I'll go through this section probably a little bit quicker, but I definitely want to spend some time on the hands-on parts because that's where it gets really interesting. Because we can do the same things that we did for language models with these models as well. I think it's useful to see that happening. Um, okay, so what are some of the challenges with working with diffusion models? So the input and the output of the unet are images, and they're images of the size and resolution of the images that we want to generate. So that's actually a challenge when you compare to language models, right? Because you saw when we looked at our the snakes have ears example uh, with the Microsoft Phi model, the input was a relatively short sequence of tokens, right? It was like, I don't know, it was like 15 tokens or something like that. It was just 15 integers representing the input I'm passing to the model. Here, the inputs can be huge, right? Like if I had a fairly high resolution image, let's say it was 1,000 pixels by 1,000 pixels, which actually isn't even that big of an image. That's a million pixels. And there's one integer value for each color channel, red, green, and blue in each pixel. So it's 3 million integers compared to the 10 or 15 or whatever I pass to my language model. So images are big, right? And so the inputs to this model are going to be big. So that's one challenge, is that you have to deal with large inputs and large outputs. Because you're dealing with these large inputs and large outputs, generating large full color images, right? Because you need one channel for red, green, and blue for if you're doing color versus black and white. Generating these large inputs can be slow, right? The models have to be big. There are lots of stages in this unet to shrink that large model down and then back up. So generation can be super slow. And then training the model also is slow, requires a lot of computation, and also has high memory requirements. Again, purely just really more than anything else because images are large, right? So this is a key challenge with making diffusion models actually useful. So so it turns out, so I guess the real breakthrough with diffusion models was this observation that you don't necessarily have to perform these diffusion steps to generate images on the raw images themselves. you can find some sort of compressed, much smaller representation of an image, and then you can work off that. And then only when you're done with that process, you can then expand it back to a full-sized image. So the fact that you can work with a compressed representation of an image and that this whole process actually produces good quality outputs is a big breakthrough in this area, right? The idea is that now the size of the inputs and outputs can be much smaller if you compress the image first. If you're providing an image as input, or you can start with something that's very small if you're doing generation and only at the very, very, very end expand it back up. So the idea here is that, what you're working with, when you talk about working with these compressed images, that's often called, you're working in what's called a latent image space. And so often when you hear people talk about diffusion models, you hear them specifically talk about what are called latent diffusion models. And latent diffusion models are, and we'll discuss a little bit more in the next slide, but these are these models that sort of work with these compressed representations of the image first. So what happens here is that instead of generating the full image, the unet generates this compressed representation of the image. And then at the very end, that latent representation is expanded into the full image. Okay, so this is the architecture of kind of a typical modern text-to-image generation system that uses diffusion models. So you have a few different components working here, right? So you have this, at the heart of all of it is you have this text-conditioned latent unet, right? So this is basically, the thing that does that denoising process. But there are a few things that have been added onto it. One, it can take text inputs to condition what we generate. It's also not working on actual images, but it's working on these compressed representations of images. So that's one key component of this. That's probably at the heart of all of this is the text conditioned unet. And that's what does this sort of denoising. Okay, but what about actual generation? So again, just like you did with an ordinary diffusion model, you're going to, where you started off with a random image, and then you just iteratively did this denoising. Here you're going to start off with a random compressed image, and then you're going to do that iterative denoising. And so the idea here is that as an input, you take your random compressed image. And so in this case, maybe that's a 64 by 64 array that we're going to ultimately expand all the way up to a 512 by 512 image. But you're going to take the 60 by 4 by 64 random compressed image, and you're going to do a denoising step. And then you're going to take that denoised one, pass it back up, do it again, do it again, do it again, right? For maybe say 30 steps, 50 steps. So another component is what's called a scheduler. And a scheduler is the thing that controls that iterative denoising process, right? You put in noise, denoise a little bit, do it again, do it again, do it again. A scheduler is basically controlling that loop. So then you have your text encoder that you're using to encode the text in a meaningful way for your text condition unet. So that's a component on its own over here. So maybe I have some text prompt that I provide in. That gets converted to something that's a meaningful input to my unet that I use for denoising. And then that output produced by the text encoder gets passed into the text condition unet. And now this gives me a way to generate a text conditioned output, a compressed output, but one that's been text conditioned on, say, a text prompt that I provided to the model. So, basically I pick a totally random input 64 by 64 array. I have an input prompt, say an astronaut riding a horse, and then I use that to do this denoising, but I guide the denoising with my input prompt so that at each step it's sort of orienting what's being generated towards something that resembles what's described in that prompt. And then finally, at the very end, I've got this compressed output that I then want to expand back out to an original image. And so finally, there's another type of model that's part of this whole architecture, something that's called a variational autoencoder that's become kind of the popular architecture for converting these latent compressed images back up to the decompressed image. And so that's sort of the full picture for kind of what this architecture typically looks like. And when we get to the point where we see this in code, I'll print out, how Hugging Face diffusers actually represents our model that we'll load when we do the part on open source models. And we'll see it has all these pieces, right? All these pieces are there in place. These are all working together in the full pipeline that's used for text generation. Okay, so yeah, a couple of questions here. I see, are diffusion models also part of LLMs? No, so this is a different class of models. Large language models are based on the transformer architecture, which in principle is different than a plain diffusion model. There are some shared ideas between the two. So when we take those the text encoding and we feed it into the unet, it uses a mechanism like attention, what we have for transformer models, to do that conditioning. So there are some sort of similar ideas behind, how what types of model components are used in both models, but really they're different. They're conceptually different things. They happen to just kind of use some similar different model components. And then how's the latency decided? Where does it come from? Yeah, that's a good question, right? Because I earlier said it was random, and you're like, okay, it can't be completely random, but the idea is it actually is. It can be totally random, right? So you can just generate a totally random um, input, and it's the text conditioning that's going to basically guide how that random input gets denoised. And so you'll see, like when you use these models, you can use the same input prompt, but I can try it out with different latent seeds, and I'm going to get different variations I'm going to get basically different outputs. All that correspond to that prompt, but the output will be different each time. And the thing that sort of guides, whether I get the same input or whether I get the same output, or whether I get a different output, whether I get a different output or the same output is really what I fed in for that seed. But it can be completely random, right? And typically that's how it's used. You just pick a totally random late input. Okay, so let's do a quick summary and a quick recap quiz on this section. This was like a quick section, and then we can move without a break onto the uh, on the actual implementation parts. I think that'll get interesting when we see how this actually works within, especially how we see how that works within Hugging Face. Yeah, so the initial 64 by 64 input image is chosen based on criteria, or how does it know which image to pick? So it's totally random. So the idea is, you could pick whatever you want, and the text condition unet is basically going to filter that into something coherent based on how the text prompt guides it, right? So the text prompt is going to sort of tell it how to filter it, and it's going to iteratively denoise it, right? I don't know. I use like for me, like kind of I don't know, sort of silly analogy is like, I don't know if you've ever you look up at the sky and you look at clouds and you say, okay, what does that cloud look like? And you say, all right, yeah, I guess it kind of looks like a car, right? You can see that's the hood right there. That's the trunk. That's almost like what these models are doing, right? They're just looking at noise and saying, hey, make this, here's a bunch of noise. Filter it somewhat so it looks like a really, really noisy picture of an astronaut riding a horse, right? And so what it would do, I mean, this is, if you weren't working in the latent space, if you're just working with the original image, it would say, okay, well, there's going to be like a dark part in the middle, and it's going to be sort of shaped like this. So maybe I'll filter it to do that, but I'm not going to like fill in the details yet. And then the model says, okay, great. Now take that and make it look like an even less noisy picture of an astronaut riding a horse. And then you just kind of fill in those details a little bit more. And you do that, I think you'd usually, typically 30 or 40 for like, for the open source models that I've worked with is sufficient to get a coherent image. But you're really starting that from just a purely random input. Um, and it's that filtering that's guided by the text prompt that's going to turn it into something coherent. It doesn't need that. You don't need to pick something clever in the input. Okay. So a quick quiz here before we move to the next sections. So let me just there we go. Okay. Yeah. So yeah, so actually let's look at a summary before we move on to that quiz. So the idea here is that the way diffusion models produce images is by denoising random noise, right? You give it totally random noise at the input. It incrementally denoises it either guided by a text prompt or because it's been trained specifically on the target class of images, and it knows from that training sort of what type of coherent image it's trying to denoise that to look like. So that denoising process is something that happens sequentially. It happens in multiple steps or stages. And those those stages are controlled by what's called a scheduler. A scheduler is basically saying, how many steps am I going to perform? It's going to control which one gets performed. And if there are certain parameters that need to be passed as inputs to the unet, the denoising model, the scheduler will set those parameters. Where this gets really interesting is when you can condition that denoising process on a text prompt. So I could say, hey, I'm just giving you complete random noise. Make it look like a picture of this, specific thing. And miraculously, these models actually do an amazing job of doing exactly that. So you can condition that denoising process on a text prompt. So in principle, this all works if you just work directly on random images as input. You directly generate and then you generate coherent outputs that are images, but it's super slow if you work directly on the original images, partially just because images themselves are large. And so the typical way to make this practical is to work on this compressed image space, this latent space. And only when that process, the denoising process, is done,